calculations. And this was the main goal for this year, to go one step further, to follow one long-term goal, namely the goal of developing a full-fledged theoretical model of cortical dynamics. And aim number one for this year was to develop a functional model of the basic modules of the cortex that support conscious processes. And these are, as we will see in a minute, the so-called cortical microcolumns. And in detail, this now means the goal is to scrutinize the feasibility of macroscopic quantum coherence in microcolumns, to show that under the conditions observed in the brain, the conditions observed in the microcolumns, it is really plausible for a phase transition to occur, to demonstrate that the operating principle of these elementary building blocks of the cortex of these microcolumns relies on the strong coupling regime, namely on the strong coupling between the neurotransmitters and the zero-point field, and to lend credence, to lend support to the notion that the brain is specifically designed to modulate the zero-point field. This is what I wanted to achieve in 2022. And so let's delve into the details.
But so, why do you need the neurotransmitters? Can't neurons
we will see
also?
This in a minute. Just let me explain, and I will give you a good reason why I think that the neurotransmitters play the key role in this dynamical interplay with the zero-point field. And it's all about concentration levels. So let's take a look at the cortex. The cortex is organized horizontally into layers and vertically into columns. And it's widely accepted that the basic unit of operation of the cortex is the so-called microcolumn. And a typical microcolumn consists of roughly 80 to 100 neurons. Most of them are pyramidal neurons, and they are equipped with branched dendritic trees. And these dendritic trees are covered with synapses, and the presynaptic terminals contain vesicles with high concentration of neurotransmitters, and the release of these neurotransmitters leads to the activation of receptors located on the postsynaptic terminals. So in summary, the cortical surface consists of a vast number of these microcolumns, actually with little variation in size, also with very, very little variation in size across all the species. And a typical diameter of these microcolumns is in the range of 30 micrometers. And now let's take a closer look at a structural model of such a cortical microcolumn. A cortical microcolumn receives numerous inputs from other cortical areas and also from the thalamus. And though these so-called cortical, and thalamo-cortical fibers connect to the synapses that populate the dendritic trees of the pyramidal neurons. And in active synapses, signal transduction takes place through the release of neurotransmitters. And then the signal propagates along the neuron, and finally, via an axonal output, the signals are transmitted to other regions of the cortex and also to the thalamus. And this is still a complex model of a cortical microcolumn. And this can be, however, translated into a more simplified model of a microcolumn, which includes only pyramidal neurons and glutamate as an excitatory neurotransmitter. And this is a very good first approximation of such a model. And why? Because the concentration of glutamate is significantly higher than the concentration of any other molecule in the brain, except water. So since the resonant interaction between matter and the zero-point field depends, as we will see, on the concentration of matter, it's a natural first step to look at the neurotransmitters because they have the highest concentration in the brain except water. These should be the key players. So if everything is about concentration and about modulating concentration, these are the first candidates we should look at when we think about the brain's interaction with the zero-point field. And actually, there are two levels of concentration in such a microcolumn, namely a peak concentration localized in the synaptic vesicles and an average tissue concentration in everything else here. Yeah? And if you look here, in comparison to the left-hand side, these so-called astrocytes or glia cells have now been removed because their primary role is to regulate the glutamate pool and to keep the glutamate concentration within a specific range. So these are now taken out and they are substituted by a tissue concentration. So this is what these astrocytes do. They regulate the tissue concentration. And in addition, we have a peak concentration in the synaptic vesicles. So looking now at this microcolumn, it's a bundle of pyramidal neurons which sit or are embedded in a glutamate container, or more precisely in a glutamate water matrix. And it makes a difference there is a difference between the tissue concentration and the peak concentration, which we have to take into consideration. So if you want to build a microcolumn in the lab, take a bundle of neurons or fibers, embed them in a glutamate container and make sure that there are pockets of higher concentration of glutamate distributed across the microcolumn. So this is a simplified picture, a simplified model of a microcolumn. And drawing on the structural model, we are now in a position to develop a functional model of a microcolumn. And in this model, the synaptic vesicles play the role of the individual clusters in which a phase transition is triggered. So to put it very simply now, the higher concentration of glutamate in the synaptic vesicles is needed to trigger, to ignite the microcolumn and to set off a runaway stage. And in this runaway stage, it's the neurotransmitter zero-point field interaction that then gives rise to the emergence of a collective state, and a collective state of the neurotransmitter molecules. And on the other hand, this resonant interaction results in the boosting of the field modes that play a dominant role in this interaction. So on the one hand, we have the resonant the resonant neurotransmitter zero-point field interaction, which leads to a vibrational excitation of the molecules. And on the other hand, we have the boosting of the participating field modes. So this is the rationale, the idea behind this model. And now the crucial question is the peak concentration of glutamate in these synaptic vesicles sufficient to initiate the runaway stage? Are these pockets, is a concentration of glutamate in these pockets high enough to trigger this process? This will be the crucial question. Can only be solved via a calculation, as we will see. And if now this is the case, that means if the concentration is high enough and this initial phase, this runaway phase is triggered or set off, then takes place that drives the entire neurotransmitter pool within the microcolumn toward a stationary coherent state. So the high concentration in the vesicles is needed for triggering off the process, and the lower tissue concentration is then needed to stabilize this process and to arrive at a stationary state. And the crucial questions here are, so given the realistic tissue concentration of glutamate, does the resonant glutamate zero-point field interaction really result in such a stationary state? Or does it collapse, or does it explode, or whatever? So is the tissue concentration of glutamate in the right range in order to produce a stationary state, a really stationary coherence domain? This is a crucial question. The next one is, does the diameter, now we can calculate, right, with these calculations, we can calculate the diameter of a coherence domain. And the question is, does this calculated diameter agree with the measured width, the real size of a microcolumn as derived from empirical evidence, which is 30 micrometers? And the next questions are, so what, does the formation of such a coherence domain entail downstream effects indicating that the glutamate zero-point field interaction is vital for the functioning of the microcolumns? So is coherence decisive for the next step, namely for the communication between microcolumns and the formation of long-range coherence? And these are the crucial questions. And to answer these questions, we have to resort to quantum electrodynamics, and we have to perform concrete calculations. And of course, I will not go through these calculations today. I will be relatively brief, and I just want to convey the main ideas behind these calculations. So what we find is that the quantum field theoretical treatment of the neurotransmitter, so specifically the glutamate zero-point field interaction, leads to a coupled system of evolution equations. And the main quantities now that go into these equations are, first of all, the occupation number of the ground state of the neurotransmitter molecules, the occupation number of the excited state of the neurotransmitter molecules. We have the A, which stands for the amplitude of the resonant field modes. These are the field modes that interact with the neurotransmitter molecules. We have the coupling strength between the zero-point field modes and the system, the neurotransmitter, the meta system. And we have one multiplier mu. This is the whole story here, the result of the calculations. And we have basically only two parameters that enter the game, namely the G, the coupling strength, and this multiplier mu. And these depend on the neurotransmitter concentration, which is number of particles per volume, n divided by V. And we have the resonance frequencies of the neurotransmitter molecules and the excitability of the neurotransmitter molecules expressed in terms of the dipole transition matrix elements. And these properties can be derived from the absorption spectrum of glutamate. Once you know the absorption coefficients of glutamate, you have the resonance frequencies and the excitability. So there is only one free control parameter in this whole game, and this is the neurotransmitter concentration. And once you know the concentration of glutamate, and once you know the initial conditions in the microcolumn, which we know, you can calculate the full dynamical evolution of the system. And there is no fiddling around and no cheating. So it all depends on the neurotransmitter concentration, which is measurable. And what we find using this mathematical toolkit is that the evolution, we can now address these questions one after the other. The first question is the peak concentration of glutamate in synaptic vesicles sufficient to initiate the runaway stage, sufficient to trigger this whole evolution process, this interaction process of the neurotransmitter pool with the zero-point field? And it turns out that the evolution equation in this case can be simplified and reduced to just one equation. And what we get is also a runaway criterion, namely the coupling strength G must exceed a critical strength GC. And now we insert a realistic glutamate concentration in synaptic vesicles. And what we find is that the frequency that dominates the whole evolution is a frequency which lies at 7.8 terahertz. And this results in this value pair for G and mu. And this leads to the following picture. So this solid curve indicates the critical coupling strength as a function of the parameter mu, and this curve separates the critical from the non-critical regime. And the red diamond marks the pair of values that come out of the calculations. And there is no cheating. That's the measured glutamate concentration in vesicles. And this is what we get. And the result can be interpreted in such a way that the coupling strength lies a little bit above the critical threshold, above the edge of criticality. So yes, the runaway criterion for the initiation of a phase transition is fulfilled. So the glutamate concentration in synaptic vesicles is precisely designed to trigger a phase transition in a cortical microcolumn. The next question is, now, obviously, the peak concentration in the synaptic vesicles, the peak concentration in a microcolumn is sufficiently high to trigger this process. The next question is, now, given the tissue concentration, which is lower and which decelerates this evolution process, does this concentration result in a stationary solution? Do we get a stationary solution, a stationary coherence domain? And here we find that the evolution equations can be written in this way. The glutamate tissue concentration is typically in the range of 12 millimole per liter. Inserting this value into the equations results actually in a stationary, very nice solution. And it turns out that we are now what we expected. We get, first of all, a coherent state, a stationary coherent state of the glutamate pool. And on the other hand, a significant boosting of the dominant field modes that play the main part in this interaction. So what we wanted to get is this result, namely a significant boosting in a microcolumn of the relevant field modes. And the second very important result is that the energy per molecule is reduced compared to the classical state, to this non-interaction state with the independent molecules. So once this coherent state is achieved, the energy per molecule is reduced, and this whole system is now energetically favored. And it produces a so-called energy gap, and this energy gap prevents the decoherence of the system.
Joachim, can I ask a question here?
Yeah.
This is, I think, quite clear, and I feel like I understand the basic outline of what you're presenting. I'm not clear, though, on why these effects, these ZPE effects, would be the critical dynamic in this particular system, when I think, based on your assumptions, every molecule in a system would actually have similar ZPE field interactions. Or is it something about glutamate in particular you're saying, because of its role in the neurotransmitter and neural complex, is special?
Yeah. Basically, yes, but the concentration is not high enough. With any other molecule, let's jump back here. This is this critical quantity that enters the whole game. For all the other molecules, this mark here would be located in the non-critical regime. Only with this highly concentrated glutamate pool in the cortical microcolumns, you get this runaway solution, and this, at the end of the day, this coherent state, this stabilized coherent state.
Got it.
Yeah, this would not work. You're right. I mean, GABA or the other neuromodulators, chemically, they have very similar properties, but their physical concentration in the brain is simply not high enough to make this possible here and to trigger this process,
Mm-hmm. Got it. Thank you. Just a
So
time check. We have about
the crucial point.
We have about 20 minutes total left, so keep that in mind.
Yeah, no problem. Brilliant, very important question. Yeah. So why not all the other components? What makes glutamate so special? Well, it's not the chemical structure of this molecule or so. It's the fact that this molecule is present in a sufficiently high concentration, and this high concentration makes this resonant interaction with a 0 point possible.
So if I understand correctly, you said that the tissue concentration glutamate is
Yeah.
important for the stabilization of it.
Yeah.
Why it's important? How come this concentration is causing the stabilization?
Because it decelerates. What we have here, the runaway stage is driven by an avalanche process. This from a field mode fluctuation around zero. By means of these dynamical equations, we get an exponential acceleration of field mode at the beginning of this runaway stage, and then we need some element in the dynamical equations that decelerates, that causes stability at the end of the day. And this is the lower tissue concentration of glutamate. Oh, sorry for all these animations here, but it's a lower. Then after the triggering, the setting off this process, we need some stabilizing element, and this is a glutamate concentration which is lower and which somehow decelerates its evolution and settles the system into a stationary state.
Gotcha. So because it's lower concentration, actually. Yeah, thanks.
And and this is also not it's not usual. I mean, it could any other concentration, and I played around with a huge range of potential tissue concentrations. Many of these concentrations do not result in stationary solutions, so it's very specific that the glutamate concentration in neuronal tissue is arranged around 12 millimole, and this is a value that balances this evolution, and so it leads to a stationary coherent state. And question number 3 is, well, we have everything here now. We have the mathematical toolkit to calculate the size or the diameter of a coherence domain. The critical question now, which we would like to answer, is, well, does it agree with the width of a microcolumn as derived from empirical evidence? So if, now the question is, if coherence plays a role in the functioning of a microcolumn, we would expect that the calculated size of a coherence domain agrees with this empirically measured or derived size of 30 micrometers. And yes, it does. Exactly for this driving mode, for the dominant field mode that dominates the dynamical evolution of the system, which lies at 7.8 terahertz, we get a calculated size of a coherence domain which lies at exactly 30 microns. And so this is at least a nice result, because it corroborates the model. The calculated diameter of a microcolumn is well in accordance with the empirical findings. Finally, the questions were, well, now, does the formation of a coherence domain, so the main point seems to be the formation of a coherence domain. The whole setup is designed in such a way, the design of a cortical microcolumn seems to be designed so that a coherence domain is formed. And of course, a crucial question which arises is that, does the formation of a coherence domain entail downstream effects? indicating that the glutamate zero-point field coupling is vital for the functioning of the microcolumn. And yeah, it is. It does result in downstream effects. The first one is the resonant neurotransmitter zero-point field interaction results, as we have seen, in a vibrational excitation component of the molecule. So part of the molecules are boosted to a vibrational excitation. It's actually, it's a superposition. The final coherent state is a superposition of the ground state of the molecules and the first vibrational excitation. And this is important because vibrational excitations induce receptor activations through vibrational energy transfer and result in conformational changes of the receptors and in the openings of channels. So the resonant interaction with the neurotransmitter pool has one positive effect. It enhances synaptic signal transduction. On the other hand, we have seen that the resonant interaction leads to, first of all, the boosting of the participating zero-point field modes, but the calculation also shows that the dominant field modes are significantly shifted to the microwave region. So within the microcolumn, the oscillating modes have a frequency of 30 gigahertz. And this is now a strong microwave field that is built up in a microcolumn. And here we know from many, many studies that microwave radiation fields have a positive influence on the ion channels and on voltage-gated ion channels. So microwave radiation modulates voltage-gated ion channels populating the axonal membrane. And this is obviously a potential way how the microcolumn controls axonal signal transduction. This is a second downstream effect. So the coherence domain has the effect of enhanced synaptic transduction and a control over axonal signal transduction. And these two effects combined, I think maybe this is not mathematically proven so far. These are just obvious conclusions from this approach. Both effects combined may be crucial for the next step, namely for the communication of individual microcolumns with all the other microcolumns and for the formation of large-scale activity patterns. So this is basically it. And this brings us to a conclusion, namely that quantitative calculations suggest that microscopic quantum effects in the brain are feasible. The presented model lends support or credence to the idea that the operating principle of these basic building blocks of the cortex, of these microcolumns, relies on strong neurotransmitter zero-point field coupling, so on resonant neurotransmitter zero-point field interaction. And, well, it at least suggests that the brain is specifically designed to modulate the zero-point field. This is no coincidence. The concentrations of the relevant neurotransmitters are precisely in such a range that a resonant interaction with a zero-point field is possible. And so the picture takes shape that long-range coherence emerges through a kind of bottom-up orchestration process involving the zero-point field. And a key characteristic of this process lies in the formation and propagation of coherence domains. So looking now at a potential, so a model and the theoretical underpinning of conscious perception, we have a stimulus, and a stimulus, what does it do? It gives rise in the brain to the ignition of selected microcolumns. Each of these microcolumns form a coherence domain. Each of the coherence domains is associated with a characteristic field mode of the zero-point field. And this, by the way, depends on the local neurotransmitter concentration. And then it's a coupling, so to speak, of these coherence domains that results in the formation of a coherent large-scale activity pattern. And it is this coherent activity pattern which is accompanied by a set of amplified normal modes of the zero-point field. And this is the place where consciousness enters the game. This is the physical engine behind it, resulting in coherence domains, coupling of coherence domains in long-range activity patterns. But at the end of the day, it is this accompanying feature, namely the amplification, the boosting of a set of field modes in the zero-point field, which makes up a unified conscious state. So this is the main idea behind it. And so far, I have been dealing, that's what I showed you today, with this, with the functioning of individual microcolumns. And the next natural extension now for the next year of the model would be now the development of evolution equations that describe not only a single microcolumn, but the behavior of many interacting microcolumns. So this is the natural next step. No? Now to study, to take the next step, to study the communication and the cooperative behavior among the microcolumns that leads to long-range coherence and leads to a set of modes that hopefully then can be interpreted as a unified state of consciousness. And this is the way to a full-fledged QED-based model of namely three things. First of all, cortical dynamics. Second, in the background, the modulation of the zero-point field, and in the long term, the understanding, the translation to the phenomenal states that are associated with these amplified normal modes. Yeah, so hard stuff. Thanks a lot for your
yeah, thank you, Joachim.
For listening.
That's great.
For attending and for your questions.
Yeah, thank you, Joachim. Jonathan, go ahead. You're on mute.
Yeah, thank you. That was really a absolutely fascinating and quite compelling attempt to connect consciousness to physical reality. So I really applaud you on that. It seems very exciting. In your discussion, you focus particularly on glutamate as being sort of a key element in enabling consciousness to cross this threshold. And I'm wondering if you think that glutamate is sort of the exclusive medium, or if you think that others are, and then also either way, sort of what the implications are for how far down conscious phenomenal experience goes. Do you think that organisms, say one-celled organisms, would be capable of, do they have glutamate in such a fashion that they'd be able to do this? Do you need a nervous system and so on? There you go.
Yeah, very good question. First, let's start with the human brain. I mean, at the beginning, I thought, well, what I knew from prior considerations and calculations that we need actually a high concentration of some molecular component. And that's the reason why I started with the neurotransmitters. And as we see, it seems to work out, and it seems to result in a very, in nice results, let's say, in compelling results. I was also asking this question to myself, and at the beginning I thought, well, I mean, glutamate maybe one example. It's about the whole pool of neurotransmitters and neuromodulators. Yeah, so we have GABA and we have dopamine and serotonin and so on. Yeah, all these molecules may play a significant role in this orchestra. But the more and more I think about it, I come to the conclusion that it's most probably only glutamate, and all the other neuromodulators simply modulate the concentration, the local concentration of glutamate. Yeah, so that's my current take on your question. Yeah, today I would say no. Basically, it's only glutamate that plays a key role, and all the other elements of the cocktail, so to speak, they simply modulate locally the concentration and the resonance frequency. But this, of course, does not yet answer the question, what about other species? What about single cells? What about microbes, whatever? And to put it straight, I cannot answer this question. One plan of me is in the future to go through all the other potential molecules and look at concentrations of potential candidates in microbes, in other species, and so on. Yeah? So the natural starting point for me was just the human brain, because this is the most important thing we know. Yeah, it is associated with consciousness.
Thank you. I'll just say that I really hope you're right about glutamate, because it makes it so much easier to, track and to make predictions than if all the different ones are doing it simultaneously. So fingers crossed on that. Great answer. Thank you.
But I will see. I will keep you updated. And but my first guess now is it's mainly about glutamate in the human brain, and all the other players are just the modulators of this one key component.
Time for one more question. Nir, go ahead.
Okay, hi. Actually, I have like two questions and a comment. I don't know if we have time or not. Comment for that. Okay, let's start with the most.
It's up to you.
Let's start with the most critical question, I guess, that I have. It's a very creative and interesting idea, and for me, it sounds like it's a very good theory of how to do a unification of consciousness. But I'm not sure if it actually solves the mind-body problem or the heart problem, because there is only an assumption here that the electromagnetic force has this intrinsic phenomenal property, but there is no explanation why, or what is it, or what is the mechanism behind that. right? So it might be true, it might be not true. We cannot, I don't think that we can prove something like that. So I don't know. This is my problem here.
Based on the theory in the it's not so easy. You're fully correct. But in the long term, I think if this turns out to be a viable approach, I think in the long term, we will be able to answer this question, because the more we know about the modification of the 0-point field, the more or the easier it will be to derive something like mapping rules. Yeah. So the more we understand which of the phenomenal properties corresponds to which normal mode of the field, we could then derive something like mapping rules, you know, and say, well, if you trigger a certain field mode of 7.8 terahertz, this corresponds to the color blue in a visual perception. Yeah? And this mode of 7.5 corresponds also to a visual perception, but to green. And another range of the 0-point field corresponds to auditory perceptions, and so on. So this may open up a new space of very in a very clear way of mapping, yeah, of setting up a mapping between a physical property of the field and from first person accounts, also mapping this to percepts, to documented percepts.
Thank you.
Yeah.
So I actually have a hard stop, but I'm going to suggest that Jonathan actually become the host. I'll make him co-host so you guys can keep on going, and I'll do that right now. So thanks so much, Joachim. I'll talk to you soon.
Cam, will the recording keep going?
Yeah, I'll leave it going. So when you end it, it will stop the recording.
Okay, very good. Colin.
Hi, Joachim. Thanks for another really interesting deep dive. I have a question. I want to raise things for you to think about. If you can imagine, we know empirically that the subjective experiences do not come from, say, the spinal cord or other peripheral areas. That it's all a central nervous system function. And yet glutamate's universal and the layering structure is universal. So what would be your account of why the spinal cord would not contribute to subjective experience, whereas the central nervous system would, when it's got the same basic architecture and the same chemistry? That would be something I would ask you to look at.
Yeah.
It would seem to me to be something that you would need to deal with. And the second thing which occurred to me was the claim that the chemistry, the concentration chemistry, I'm not sure whether the criticality of the actual absolute value of the concentration was the key feature or not, but the actual most dense substance in the all of it is actually the membrane. The lipid bilayer with its two the SN3 legs, the lipids themselves, and the head group, the lipid legs are highly compressed and they're immersed in a gigantic electric field. It would seem to me that the coupling between that and the 0-point field would be substantially different to everything else in the tissue, and that it in and of itself and its variability in terms of the variability in the actual lipids that are used, and they form a mosaic pattern of implementation over the surface area of the cell. That to me, and the disruptions to it, which are huge when the field system undergoes massive reversals during action potentials, would seem to me to be a really good place to examine coupling between the neurons and the 0-point field. And I just sort of wanted to raise that as something for you to think about. It's obviously not going to be accounted for here and now, but you know, the membrane literally excludes all the water. I mean, it's as a concentration, it's massive, and they're also highly constricted into certain forms. You know, the acyl chains are all interlocked with each other in a kind of solid mass. So clearly it would be capable of having some kinds of resonant modes favored over others as a result of the restriction in space. And that to me could be very significant.
Okay.
So I just thought I'd raise that while I was here. I'm sorry about the voice. I'm just on the tail end of COVID. I haven't quite got over it yet. So anyway, I'll leave that there for now, and it's too much to go into for the minute.
Okay, thanks for the ideas. Yeah. Got it.
So these will be the last two questions freely. Or no, actually, I think Maria is next, actually. My apologies. I think she was next.
I think Freely was before me.
Oh, Freely was, okay, sorry.
Yeah, I
Freely.
don't want to jump the line.
My bad.
Hello. I just want to start by saying that I'm overall sympathetic with this approach and this theory. It's congruent with direct experience through deep meditation, where I guess there's a little bit of dissonance for me is in the exclusive focus on glutamate. And so I've got a kind of few part question. The first is just to confirm that the implication is that these coherent domains only exist in relationship to glutamatergic neurons.
Yeah, that's as I said, it's just a starting point of all these calculations. I haven't gone through all the possible or potential candidates that may play a role in this dynamical interplay with the 0-point field, but one, as I explained, the glutamate water matrix is one key candidate because of the highest concentration levels, which we find in human or in brain tissue. And maybe I should add that this does not yet rule out that some other molecular components may also be involved, particularly be involved in the propagation of coherence domains or in the building up of large-scale coherence. So this was simply for me the natural starting point for the whole model. And as I tried to convey, it makes sense, obviously, and leads to very compelling results, I think. But it definitely needs further studies to think about other components as well, and to try to understand their possible contribution in this overall orchestra and orchestration of large-scale coherence.
Well, so it seems to me that there's the implication of a kind of emergence, same with the heart problem of at a certain point, there was a certain concentration that developed, and then this coherence suddenly came into being. Doesn't that just kind of kick the can down the road?
No, the crucial point is that we are here not talking about the generation or the emergence of consciousness itself. It's there. It always has been there in this picture, but it could not be harnessed. It could not be used before such a microcolumn, let's say, has been put into place. And this is a product of biological evolution. So only, or let me put differently, not before such a high level of such a highly developed organism has existed, yeah, not before this has existed, there was no concrete conscious experience before this level, yeah, so to say. But the basic element in the universe, the very existence of a background of consciousness, has always been there. Yeah, and now higher and higher developed organisms play the keyboard of this background field and give rise to the emergence of more and more complex, concrete conscious states.
Mhm.
So that's my picture behind it. Yeah? But it's not that in this approach I would encounter the hard problem, because in my understanding, the hard problem is about the emergence of consciousness from an insentient background. Yeah.
Okay. Yeah, so given that the highest concentration by several orders of magnitude is water itself, and given the evidence for quantum coherence in single-celled organisms and organisms without nervous system, it seems to me more parsimonious that there's a pre-existing coherence that's based in the dynamic structure of water and its interaction with proteins and ions at a more fundamental level of life, and that the concentration of glutamate and the structure of the microcolumns are as they are because of this pre-existing coherence that occurs, and that's the way that this was kind of bootstrapped or expanded to allow for the cortical dynamics to occur. So to me, it seems that you know that what you're saying would apply to the cortical level of consciousness, you know, the modulation of our conscious experience through the structure of the cerebral cortex, but that there's a step that's kind of been maybe skipped over, which has to do with water itself and this more fundamental underlying, like in the work of Gilbert Ling and Mei-Wan Ho, where there's this pre-existing coherence that occurs, but there's just more levels of elaboration.
That's a brilliant comment. I absolutely agree with you. So I think life is a hierarchy of coherence domains. And I fully agree with you that at a lower level, at a more compressed, more condensed level, there is some rudimentary form of consciousness at the water level. Yeah? And I didn't talk about it today, but the same, what you said, the same mathematical toolkit could be applied to water itself. Yeah? And we could study coherence domains arising from water molecules, and this would lead to much lower dimensions. Yeah, and these may be the basis for the next level of coherence, which is established in the human cortex. And I absolutely agree with you. Yeah? At a lower level, at a more rudimentary level, concrete, simple conscious states could have evolved at the water level. Yeah?
Thank you.
Great question, Philly, and that actually really built nicely on mine in fleshing out the water element. Maria.
Yeah, thanks. Really wonderful talk. And yeah, the glutamate thing is interesting to me. There was that paper I posted in the chat that was just recently published showing that glutamate levels in different parts of the brain are actually correlated with senses of unity during psychedelic experiences. And there's actually some different qualities of that might be separated by where that glutamate is in the brain. But my question for you was actually about the terahertz. So, you know, this is super interesting to me because there are so many biological effects that have been demonstrated in the terahertz range, from neuronal effects to hippocampal effects to just weird neurite growth that can happen. And I was wondering, you know, what your thoughts were on that, and also just on any implications this might have for safety, and in terms of the fact that we are using terahertz so much for communication?
Ooh. Yeah, again, the crucial point is that when we look at this at the interaction of matter with the 0-point field, the 0-point field is not any field, you know. The 0-point field has a very specific structure, and this structure enters these equations. Yeah. So, for instance, it's scale invariant and so on, and this implies a certain regarding the frequency components, a certain structure of the field. Yeah, and this is not comparable to any terahertz field that may be produced in an electric device or so. So it needs this specific, for instance, it's omega, it's frequency to the power of 3, which is a very important component of the energy density of the 0-point field and so on. And this enters in a very critical way the calculation. So it would, I think, not work with any terahertz radiation as long as it is not the 0-point field, you know. It's a specific internal structure of this field that gives rise to structural, to emergentism, so to say. Yeah, it builds up something, and which is not possible with any other field. You know what I mean? I mean, it's this specific physical property of the 0-point field that is obviously a creative field in the universe, that makes it build something which is not possible for any other structure.
Okay, I think on that, we'll close it. Let's again give a round of applause to Joachim for really a spectacular.
Thanks a lot for listening, for your patience.
We look forward to having you back in a year and hearing the progress.
I want to hear the next one.
Right. We're, do you have?
Thank you very much.
Is there a paper?
Yeah, I will send you a link to a preprint. The paper is currently under review, and there is a preprint, and I will share the presentation if you like, the PDF of the presentation, and a link to the preprint.
Perfect. Thank you so much. Bye, everybody.
Bye, and thanks a lot.
Bye-bye.
See you.
Can I send you an email, by the way, with a couple of questions?
Yeah.